welcome to our today's learning. I'm your facilitator, John Gekonyo, and we shall be looking at Actuarial Mathematics 2. And our lecture today will involve survival, distributions, and life tables. So I will introduce life tables, and then we shall look at survival probabilities. So some key objectives that we shall aim to learn include how to use life tables and also to calculate survival rates. So we'll be able to use alternative source of data to construct life tables, describe life table functions, and various actuarial notations that we shall use. We have L subscript X, then we have dx, so X is the subscript, and the select equivalent, LX select plus R. Then we'll be able to express life table probabilities in terms of the following functions. We have N a subscript P X a subscript, and then we have NQX, and then we have N, and this is a vertical bar, not a slash, vertical bar MQX. And we'll also be able to look at the select equivalent. So we'll be able to look into detail how we interpret each of them, and also look at the force of mortality, describe the property of the distribution of future lifetime, and introduce some bit on catet, future lifetime, catet, and future lifetime of random variable. Maybe we can define what is a life table. And in actuarial science and also in demography, a life table is a table which shows for which age what the probability is that a person of that age will die before his or her next birthday. And a sample actuarial table will be like this. So this is a sample extract from an actuarial table. So we have the first column now, which is the age. And we'll be able to know what we then we have the second column, which is denoted by LX, to be able to understand what we mean by that. Then we have DX. And we have different forms of life tables. For example, what we have here is what we refer to as a single decrement table. What is recorded is simply the age and the number of lives. So the decrement from such a table is only as a result of death. So you can note that the values are decreasing, the number of people are decreasing. So the decrement is as a result of death. Then you can have multiple decrement table. So this is simply a table in which, so the number of deaths resulting from different causes is noted. For example, from the first cohort of people under investigation, we can have the number reducing because of cause 1, death. This can be an illness, accident also, cause 2, cause 3, and so on. Then we have multiple decrement or multi-state and increment decrement table. So this one will not only try to observe a certain population, those that die from a certain illness, but we'll also try to look at also those that change from one state in life to the other, for example, marriage, and those that change from one location to the other. We can also have something like migration, and so on. And that is what we refer to as a mode state and increment decrement table. So in our conventional life table that we had in the example, so the table conceptually traces a cohort of newborn babies through their entire life under the assumption that they are subject to the current observed schedule of age, specific mortality rate. So we had, for example, what we had a starting value of 100,000, and then at each and every age, the number that is alive is recorded. And from there, we shall be able to know how we can even compute the probability of survival to a certain age, death, and so on. So basically, in a given conventional table, in this case, the standard actuarial table, we can have the following columns. And the columns, one of them can help in getting the other one, but some may be important than others, or they may be mandatory than others. For example, age and also the number of the number alive at that particular age is also important. So we'll see how we can come up with this N dx. So N and X are subscript, and then we'll also see how we can come up with that, this and that. So either can be obtained from a given table. So note that the subscript before a symbol defines the width of the interval. For example, this one. Whereas the subscript after this one, X, defines the age under investigation. So some symbols or some notations, LX, TX, EX, will never have a left subscript on the left. So this is the lowercase of the letter L. So we will need to understand some few terms that we will use. So one is the age difference or the age interval, and this would be the interval from one age to the other. For example, here we have between ages X to N, and then we can denote it by X, comma N as a presentation in form of a coordinate. Then we have a common notation in actuarial science, which is the subscript N, then we have lowercase letter q, and then we have an X. And this denotes the probability of dying even in the interval X and X plus N. Or simply, the probability that arrive at X will die in the next X plus N years. Then we have LX, so this is the lowercase of the letter L subscript X, or simply L into bracket X. So normally this is the first entry, and it is a vital entry in an actuarial table. So after the age, we have LX, and it indicates the number of people alive at that particular age. So the first entry to that column is called a radix, as we've seen. So we can also define that as the number of survivors at a given exact age. For example, L20 denotes the number of survivors at exact age 20. So in our case, from our example, the radix, the first entry is 100,000. Then we have NDX. So this is the number of deaths to the radix between the exact ages X and X plus N. So since all the members of the radix die sooner or later, the sum of the NDX over all ages will equal to the radix, or the original number under investigation. Remember, when we talk of death, so this is a certain event in future, and the chance that a life will die is 1. So if this given population will be observed over a given time, no one can live forever. The sum of that NDX will sum to the ladix, or the original number under investigation. Then we have N capital LX. So this is person years lived between exact ages X and X plus N, or the expected years lived between X and X plus N. Then we have TX, T subscript X, and note that here T is capital. So this is the person years lived above ages X, or the expected future lifetime of a given life. Then we have E subscript X. So this is the expectation of life at age X, and it is given by the average remaining lifetime for a person who survives to age X. We will also have another one that will be denoted by E superscript. So E superscript not here, and then we have subscript X. And we'll be able to see how we define that. So it is worth noting that NQX, the conditional probability of death, so the probability that a person aged X will die in the next X plus N, is a basic function in a life table. And in most cases, life tables will have the first column, which gives the age, the second column, which gives the number of lives, and also the column NQX. So the next thing, we shall look at the mathematical derivation and the relationship between all those actuarial notation that we have mentioned, that is NQX, NPX, EX, and many other. And before we can continue, I want us to define some things that we should put them clear. So when we refer to X, so this would be the random variable for age at death. The probability density function of f of X will be denoted by a small, the lowercase of letter f, then the uppercase will denote the cumulative density function. And from probability, we remember how to find the cumulative density function, which is given by the integral from 0 to x of the probability density function. And it is worth noting that the probability that X is greater than X is simply the probability of survival after age X, and which can be shown to be this. Then we have the conditional probability between ages X and X plus N, and which can give us the NDXN. So I want us to look at or to introduce these probabilities as we have defined them in detail. And when we refer to as N to as T or N, in most cases, some texts will work with NPX or TPX. So this is simply the probability that a life aged X survives to ages X plus T. So P denotes probability of survival, then Q will denote the probability of death, probability that X dies between ages X and X plus N. So when T or N, depending on what you've written, is 1, so normally we omit it, and we can simply have P subscript X and Q subscript X, but then this is the probability that X survives for at least 1 year or survives in the next X plus 1 years. So from the actuarial table, so this is how we work out P subscript X, and this is given by L X plus 1, so the number of survivors at that age, X plus 1, over the number of survivors at age X. Qx is simply given by 1 minus this, which is simply Px. And you can note that if we take the LCM here and work it out algebraically, at the top, as we'll be able to define dx as Lx minus Lx plus 1, we'll have Lx minus Lx plus 1 all over Lx. And we can simply say that Qx is simply equal to dx all over x plus 1. So normally we define dx as the expected number of deaths at age x, last birthday among Lx lives. So it is clear that from what we've seen, Tpx, T subscript and X subscript plus Tqx is supposed to give us 1, because this is the probability of death and this is the probability of survival at any given age. So we can write our expressions for Tpx and Qx in terms of survival function, Sx or Sx plus T, which can also be expressed in terms of Lx plus T and Lx plus 1. Then there is what we refer to as the deferred probabilities. Here we have M, and then we have a vertical bar, and this will indicate deferment for M years. For example, when we have M, a vertical bar, then NQX, so this denotes the probability that X will die between ages X plus M and X plus M plus N. So if we are observing a certain life, X, aged at age X now, so if this is M, so we are talking of deferring this event from happening for M years, and then the person may die at the end of or between the ages X plus M and X plus M plus N. So this mathematically, this is how we find a life, the probability that a life die before ages X plus M plus N and ages X plus M. So we have the numerator X plus, we have L, the subscript X plus M, L X plus M plus N, all over Lx. So this may be remembered by following this rule. So of Lx lives aged X, Lxm minus Lxm plus N is the expected number of deaths aged between ages X plus M and X plus M plus N. So if N is 1, just like in the previous cases, so we normally omit 1, and we can simply write as probability that X will die between ages X plus M and X plus M plus 1. So here we have a 1 which we've omitted, and you've seen that it is simply dxm X plus M over Lx. So we can note that there is no such thing as M, then vertical bar NPX, because in real life, we've said that This is the probability of survival. This is the probability that arrive age certain arrive age and X will be alive in the coming X plus N years. There is no way that a given life can fail to exist and then reappear at a certain point. So we don't have such things as so. However, we can simply express deferred probabilities in terms of both survival and probability of death. So I want us to look at an example here, and we will try and work out some questions. So we have a table, and we want to find L40. Then we'll look for the probability that arrive currently at X exactly 30. Alive age exactly 30 dies between ages 35 and 36. Then we'll look for N paid 30 and 5Q30. So this is how we go about it. Note that L40 from our table, the last value is L39 and D39. But from our formula, we know that D39 is given by L40 minus, it's given by L39 L40. So this is where we obtain a formula to work out for L40. So making L40 the subject of this expression, we will have L40 is equals to L39 minus L39 minus D39, and that is giving us 9,453.97. Then we have the probability that alive currently aged exactly 30 dies between ages 35 and 36, and using actuarial notations, so this life is currently aged 30. So if I use this illustration, so this life is currently aged 30, and the life dies between 35 and 36. It dies between ages 35 and 36. So there is a defer period here, and the period is 5 years. So when we write that, we shall write it like this: 5, then a vertical bar. Then so the life dies in the next 1 year. So this is still okay. Or we say that when this value is 1, we can omit that, and we can simply write this. And we've said that this is given by R35 minus R36 over R30, and that should give you 0.0552. So the L values that we are reading are these. L35 is here, L36 is here, and then we have L30 10,000. Then we have 10 subscript 10 P30. So this is simply L40 over L30, and we have those two values, 9453.97 over 10,000, and you can see it here. So this is given by this divided by that, and that is what will give us the probability that arrive aged X, arrive aged 30, dies in the next, the probability that arrived at 30 will survive in the next 10 years. Then we have 5Q30, that's the probability that arrived aged 30 will die in the next 5 years, and that is given by L30 minus L35. So there is a correction to make at this point. So this is L30 minus L35. So this is 35 all over L30, and that is giving us 0.0217. So for an exercise, we can try and answer the following questions. So write the symbol for the probability that arrive age 52 write the symbol for the probability that 52 lives to at least 77 years. So we have P, and the age of this person is 52. And this person lives to 77 years. So we have 77 minus 52. That is 25. So that is 25p 52. So you can try and find the write down the other expression following the same rule that you've used in our previous example. We will look at the expectation of life, and under the expectation of life, we will define and also give the notation that we shall be using. So we first of all let T, the capital T, to be the future lifetime, and this is in years, and including fractions of X. So the mean of T, which we denote by, this is E, then we have a superscript node similar to what we have in degrees Celsius. Then we have a subscript X, and this is what we refer to as complete expectation of life at a given age. Note that lives don't necessarily live whole years. So death may not necessarily occur when a given life is celebrating their birthday. So the number of years lived may not necessarily be whole number. So we can have fractional years, and this takes into consideration that. So we get the complete expectation of life for a given life, and it is given by expectation of the mean of T, which is simply the integral from 0 to infinity, T multiplied by Tpx mu x plus T. Although we have not mentioned this, this is what we refer to as the force of interest, but to be able to look at that. So the upper limit of the integral can be replaced by, so note that lives don't live forever. There is that upper limit in human lives. So omega minus x, and what we end up with is that the complete expectation of life is given by the integral of 0 to infinity, then Tpx. This, note that this should be a subscript, T subscript of P, and then you have a subscript X. We can prove that, however, we will like you to check that out and find the mean and the variance and prove that the values given are correct. Then there is what we refer to as the catet future lifetime, or the catet expectation of life. And the catet expectation of life is simply that whole number part of the complete expectation of life. So if a certain life lives to ages 20 and a half or 20.375 years, the whole number part of that particular life, which is 20, is what we are referring to as the cadet expectation of life. So this is, note that the cadet future lifetime of X is simply the greatest integer. You don't round off to the next year. So this is the greatest integer to that particular life. So the number of future years completed by X prior to death is what we can simply refer to as the cadet future lifetime, or the cadet expectation of life. So a couple of formulas are used, but I would like you to look at this. So this is how we approximate the cadet expectation of life. And it can be shown that the cadet expectation of life, which is denoted by E subscript X. So here we don't have the superscript as in the future expectation of life. It can be shown that E of X is given by, so this is the summation of the individual life, and at any given time, so the death is deferred for that year, and then the probability that this life survives to that age and then corrupts and die in the following age. So there is something that we can prove that E of X, which is that, can be equal to that. Before we can prove that, I want to introduce the force of mortality. And this force of mortality can be thought as a probability of death at a particular instant, given survival up to that point, or the instantaneous probability of death. So this instantaneous measure is such that it is rather not an interval measure, and it's given by, or denoted by, mu x subscript x, and it's given by the limit where HQX is the probability that X survives to, X dies in the next X plus H years. So in terms of life table functions, so this is how we prove that, so that mu X is given by the limit as H approaches 0, 1 over H multiplied by L subscript X minus L X plus H. And we can show that mu X is equal to negative inverse of Lx multiplied by the derivative of Lx. And remembering that, recording how we differentiate logarithmic functions, then we can say that mu x, which is negative 1 over Lx d over dx Lx. So here we have a reciprocal and then the derivative of that. So this can simply be written from how we integrate or how we differentiate logarithmic function as negative natural log of Lx. So in terms of the probability density function and the cumulative density function, that is the small, the lowercase of fx and the uppercase here, we can say that mu x is given by fx minus 1 all over 1 minus fx, and in terms of survival functions, then it is given by that. So those four notations that we've introduced can be expressed in terms of the other. So we have the probability of survival, Sx, or simply TPx, and then we have the cumulative density function, and that is the probability of the probability of death. And then we have mu x. We can use either relationship and find the corresponding. So if we have mu x, we can express it in terms of fx by having fx all over sx and so on. So note that if the force of mortality is constant, for every age x, it is possible to show that Sx is equals to e to power mu x, and Tpx. This should be a subscript t here. Px is equals to e minus mu t. So the solution is as given. So we are supposed to have exponential negative the integral of 0 to x of mu t with respect mu dt, that is mu with respect to t, and this is what we get here. Tpx, it can be shown that it is equal to e to power negative mu t, and to put it in a better way, we've said that Tpx so from our first example, Sx, we've seen that is simply e to power negative mu x, or simply what we have inside the brackets here. So we can say that the numerator should be negative mu. In this case, x plus t. So this is x plus t. And then the denominator we have e negative mu x. So using the row of indices, we can simplify what we have here in this form. So we have e multiplied by e negative mu t all by e mu t. So simplifying out, we end up with what we have in this case, negative. I'm sorry, here we have, this is t, so this is x. So that cancels out, and we have e negative mu t. I want us to look at some two questions and see how the given constant force of mortality can be expressed. But before we can do that, I want us to prove a theorem or an expression that you mentioned. We can show that the catheta expectation of life can be given by the summation of the given series as follows. So we know that Ex, or the catheta expectation of life, can be written like this: dx plus 1 all over Lx. So this is the number of deaths in that particular age, x plus 1, plus 2 dx plus 2 all over Lx plus 3. So the denominator can easily be factored out as follows. So we have 1 over Lx So we have a series here, an increasing one. So we have and simplifying this can be rewritten like this. One over Lx dx plus 1 plus dx plus 2 plus dx plus 3 plus all the way, and then plus. So here we had a dx plus, we had 2 dx plus 2, so we have dx plus 2 plus dx plus 3 plus all the way. So we have already taken care of the dx plus 2, but dx plus 3 were 3 of them, so we can have another series here that starts at dx plus 3 plus dx plus 4 plus. So this series here will be changing the starting point. So what we end up with here is something that looks like this: Lx plus 1, Lx plus 2, plus Lx plus 3, all the way all over Lx. And hence, we can say that that is our proof. But maybe someone can ask, how did we arrive at this? So we know that Ly, or simply, we know that Ly can be given by L, y minus Ly plus 1 plus Ly plus 1 minus Ly plus 2. And this series continues. And simply these are simply dy plus this dy plus 1, and so on. So we end up with our original series that we had. So that is basically a simple proof that we can show that. So then there is something that I want us to investigate here. So when you're dealing with constant force of mortality, and so in our subsequent lessons, we'll be able to look at assumptions when working with force of mortality or when dealing with mortality probabilities. And one of them is the uniform distribution of death. That means that the probability of death is not affected by age over a given period of time. So if we are observing a life aged 2 and another one aged 45, hypothetically what we mean is that the chance of death on either of them will be the same. So that is what we mean by constant force of mortality. However, in real circumstances, this may not be the case, because a life age 45 has many risks, and we have risk exposure such as illnesses such as diabetes and many other forms of illness that occur as a result of death. It's not necessarily that diabetes may not be a risk factor for this life age too, but there are many other factors that this life may be exposed to compared to this life. So in our question, we want to find the probability. We find that is the computed expectation of life for life age 0. And the complete expectation of life for life aged 50 if the mortality of, or if the force of mortality is constant. So from the schedule, from the table that we had, we can easily find the future lifetime by using this by integrating 0 to infinity, then the probability that a life survives to age t dt, and this is simply the integral of 0 to infinity, so exponential, because we know that to find tp, x simply exponential to power negative integral of mu t. So here we will have negative mu t dt. And what we end up with, if we integrate this, so this will give us negative 1 over t. Remember how to integrate exponential functions. So we retain this function. So we have e negative mu t, and this should be divided by the derivative of this part, which is negative 1 over mu. And then we are supposed to remember to, so this is what we refer to as a definite integral. So we should remember the limits 0 to infinity. And so if we plug in infinity here, so that is 0, then we plug in 0, we have 1 all over mu. So this is 0 minus 1 over mu, and that gives us 1 over mu. Then we have this one, which should be given by the same. But note that this probability of survival is also given by mu dt. So we'll end up having the same thing. And simplify, just like we've done in that case, we have negative mu t all over negative 1 over mu, and putting our limits for the integration, we end up with 1 over mu. So it is worth noting that if the force of interest is constant, the future expectation of life does not change. It remains the same. And this can be applied in the following example. We can have another example. And here we are finding so we have various probabilities to look for. In a certain population, the force of mortality equals to 0.025. at all ages. So we will assume that there is no upper limit for our age, and that allows us to integrate from 0 to infinity because the upper limit is not defined. So given the constant force of interest, so I want us to look at to see how we can calculate the probability that a newborn baby will survive to age 5, the probability that arrives aged exactly 10 will die before age 12, the probability that arrive aged exactly 5 will die between ages 10 and 12, and also see how we can find the complete expectation of life and the cadet expectation of life. It is very simple. So the first one, so to find the probability that a newborn baby will survive to age 5, we need to write our expression in terms of the actuarial notations. So let us start with the first one. So how do we write that? So this is arrive age 0, surviving to ages 5. So note that P denotes the probability of survival, whereas we said that Q will denote the probability of death. So this will be given by exponential, and then we have the integral from 0 to, so the negative integral of 0 to 5 is 0.025 dt, and this is given by E negative 0.125, and computing that, this is approximately 0.88250. So note that the rules of probability will always hold. Whenever you find that the value that you get here is less than 0 or greater than 1, then you should know that you don't have the correct value. Then we have Roman 2. So we want to find the probability that a life aged exactly 10 will die before age 12, and we can write that using actuarial notation. So probability of death, automatically you should know that you will have a Q. So this life is age 10 and will die before age 12 in the next 2 years. So we can compute this. Remember, we said that probability of death and probability of survival has a unique relationship. So we say that TQX plus TPX, this is given by 1. So this one can be given by 1 minus 2p10. And this can easily be obtained as follows. One minus exponential to power negative integral of 0.025 with respect to t, and the limit 0 to 2. And this is giving us 1 minus exponential to power 0.025, negative 0.025, not 25, but exponential to power negative 0.05, and this is giving us 0.04877. The value can tell whether in the near future this person has a higher chance of surviving all the chances rho, and we can tell that the chance of survival for this particular life is very high because we have a very low probability of death. Then the other one is the probability that a life aged exactly 5 will die between ages 10 and 12. So this life is aged 5 years. But then we want to compute the probability that this life dies between ages 10 and 12. And this is in a near future. So this is the life now. So this period here is deferred. This period is between 5 and 10 is deferred. So we defer death for 5 years. Then the life will die in the next how many years? 10, between 10 and 12, 2 years. So we can compute that as follows. So we can compute this as follows. So we have 5 2q5, and we saw that it is possible to express probability of survival and probability of death in terms of it's possible to express deferred probability in terms of probability of survival and probability of death, and this is how we can write this. So this is the same as 5p5 because this life will survive for the next 5 years, but in the course of the next 2 years, and this time this life is already 10, this life dies in the course of the 2 years. So this can be given by exponential to power negative 0.125, because this is something that we've computed, since it will be given by the integral, the exponential, the integral of negative 0. So the limit is 0 to 5, 0.025 dt. That was in our first example, or in Roman 1. And this is similar to Roman 2 that we've already computed, which has given us 0.0. 4877. Therefore, to simply work it out first, since we have been able to relate with our previous 2 questions, so we can simply multiply the 2 values. And when you multiply, this gives us 0.04304. A lower probability, a high chance of survival. Then we have Roman 4, and this is the probability, no, the complete expectation of life. And the symbol, this is something we've defined, has been E subscript 0 superscript node, or as this is a symbol. So this is given by 0, integral of 0 to infinity, tp0, and this is something that we've seen how we can come up with the complete expectation of life for a given life. And this is given by the integral from 0 to infinity, exponential 0.025 with respect to t. So this was exponential negative the integral. So when you integrate that, So you have negative 0.025 t dt. And when you simplify, what you have from when you integrate, so normally exponential function, so this retains, and then you divide by the derivative of what you have as the power of e. So this is negative 1 over 0.025. And this is multiplied by and the limit is 0 to infinity. So what you end up with is 1 all over 0.025. And this is giving us 40. So the expectation of life for this particular life, or the average as we defined, is 40. Then we have the catet expectation of life, and the catet expectation of life is simply defined as the integer part of the complete expectation of life. But in our case, we can easily approximate the catet expectation of life, which is said is denoted by E subscript 0, and as a discrete value, so we use summation. Then we have k, so the probability that this life is 0 will die in the next k years. So this can be simplified and what we have is something like this. Because this one can be obtained by exponential to power negative the integral of 0.025 dt or dk, depending on what you use. So this one will form a series, as you can see. If you plug in 1, so you'll have e to power negative 0.025. When you plug in 2, all the way to infinity, and that will take the form of a GP series. So the summation to infinity of that series will be negative 0.025. The numerator 1 minus, so this is in the denominator, negative 0.025, and this is giving us 39.5. So there is a fundamental relationship between the catet expectation of life and the complete expectation of life, and this is, since the two are related, we can approximate one from the other. So there are many more ways in which we can approximate probability of survival and the complete expectation of life based on various other assumptions. So this is simply a uniform distribution of death, as we'll be able to say in subsequent lectures. But we have only looked at the constant force of mortality, and as you've seen, in some cases, when the force of mortality is constant, the expectation of life for any given life, either young or newborn or old, for example, in our case it's 50, does not change at all. So the other cases that we shall look at will involve those other assumptions, and we will also look at the select life. This is under select life in actuarial tables and many others. So I'd like us to stop at that, and thank you for your listening.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.